Question number 23. Assume that the Earth revolves in a circular around the Sun. Suppose the gravitational constant g varies slowly as a function of time. In a particular, it decreases half of its initial value. That means g decreases half of its initial value. Maybe if you are taking g equal to g prime, after millions of years it decreases its half value. So in of course 1 million years, then during this time what would happen to the radius of the earth? So that the thing we are going to solve in the next section, next slide. So from the problem they are given g is varies, the gravitational constant g is not a constant, it's vary as a function of time. So it's a slowly function of time, so it decreases half of its initial value, of course, in 1 million years. So after 1 million years the g has to be decreased, g by 2, you can call this is a prime, g prime. So after 1 million year, what is your gravitational constant means, it's a g by 2. First, we want to know the total energy of the system, the planetary system. You can represent it should be equal to half time m or dot square. It's a kinetic energy. The potential energy is equal to the effective potential energy. It's L square. This is a L means orbital angular momentum of the planet divided by 2m r square minus g m divided by r. This is a effective potential of the, this is, you can call the effective potential of the planetary system. The minus gmm divided by r, it's a attractive potential because it's a negative sign, that has to be compensated with that L square divided by 2m r square. Due to the orbital motion there is a potential energy. Suppose if this potential energy is zero, that means due to this attraction the planetary will fall, the planet will fall into the sun. That means suppose if we are taking the center of the sun, this potential energy, the due to the orbital motion there is a potential energy, it will product the planet to fall inside the sun. That means it's compensate the attractive potential energy. Here g is as a function of time, it's vary, so you can call it's dE by dt. And E is not a constant quantity, it's varying with respect to time because g is varying. So this is not equal to 0, that means it's a function of time, it's varying with the function of time. Now what we want to know means, for the circular motion, for circular motion, perfect circular motion, so for circular motion this potential energy, the attractive potential energy, should be equal to the potential energy arises due to the orbital motion of the planet. So you can call L square by 2m r square. This has to be equal to g m divided by r. This is one part we got to understand. From this relation, one you can what you have to do, if the orbital momentum is constant, this is also constant, this is also constant, so one can conclude, you can combine all the what is the relation between the radius, because radius is varying, g is varying, other quantities are constant, so you can do the, it's 1 by r is proportional to g, you can cancel 1 r here. That means here the gravitational constant is inversely proportional to the radius of the, this is the orbital radius of the planet, or r has to be inversely proportional to g. This is a relation we are getting from the effective potential energy information. So now what they are given, after the millions of year g has to be reduced to of, so what is the new radius, the orbital radius of the planet? So first initially, suppose at a time t equal to 0, the planetary radius at you can call this is r1, it is equal to 1 by, you can call this is like g. So after million years, this is at a time t equal to 0, that means initial time. Now for starting time, after million year, what happened to the g means it's reduced into half.
So what is a new orbital radius? This R2 we want to know. So the new gravitational constant you can call G prime. Already we told what is the G prime is equal to G by 2 after million years. So if you are substituting here, it will give 1 by G by 2, or if you are inverting that one, 2 by G. So this is a new orbital relation with respect to the then actually we should not put equal, it's a proportional. We have to put it is proportional, it is proportional. So what we have to do now, you can divide these two equation. This is a R1 equation, you can call this is 1, this is 2. Suppose if you are dividing these two equation, we will get the relation between the initial orbital period to the final orbital period in terms of the we can, because G will get cancelled. So if you are dividing this to R1 by R2, that should be equal to, this is 1 by G, this is 2 by G. So you can cancel this G, this C, this is equal to 1 by 2, or else you can just, if you are rearranging this one, it will give R2 equal to 2 R1. That means R2 is a new orbital period after 1 million year. So the new orbital period is twice that the old orbital period. If you are increasing the gravitational constant, sorry, if the gravitational constant has to be decreased by half the after million years, then the orbital period has to be increased twice the original orbital period.
From the above calculation, we found that the radius of the Earth orbit, its new radius would be twice the old orbit radius. That means the radial orbital radius that will be twice time the original, the initial orbital radius. So this would be the answer. The first one is right.